Okay, so it's 1 p.m. So I guess we should sort of start. So yeah, so this session's on Nowcasting, and I guess our first presenter is Paul. So Paul, go ahead to share screen.
Thank you.
Paul, do you want me to give you like a 5-minute warning or something?
Yes, 5 minutes before the end, please.
Yeah, all right, no worries.
Hi, everyone. So in this presentation, I'm going to go through a new method to improve the uncertainty attached to GDP nowcast. But first, why do we nowcast GDP? Well, GDP is the main measure of economic growth, and it's used by policymakers and economic agents to make their decisions. And it's computed by national statistics offices using a wide range of data sources. But this comprehensiveness comes at the cost of timeliness because GDP is typically published with an important delay. So for instance, in the US, quarterly GDP is published about 1 month after the end of the reference period. And in the UK, monthly GDP is published about 6 weeks after the end of the month. So for economic agents to have an idea of the GDP number and make their decisions, they need to forecast or nowcast what would be the GDP number. And in order to do so, it's possible to use series which are related to GDP, for instance, like unemployment, but which are released more frequently and more rapidly. For instance, unemployment, it's typically published weekly or monthly and only a few days after the end of the reference period. So if we manage to capture the relationship between these related series like unemployment and GDP, then it's possible to update our estimate of GDP every time we have new information on this related series. And this is, so the way we capture the relationship between these series is using nowcasting methods, because since GDP is typically quarterly and the related series are more frequently like monthly or weekly, then it's necessary to use methods that allow you to model this mixed frequency data. And then also, since there is a delay in the publication of GDP and the related series are published on different time lags, then we need also to have an estimation method that allows us to account for missing values. And so that's why nowcasting methods are useful. So here I'm showing an example of a GDP nowcast. So it's the New York Fed GDP nowcast for the first quarter of last year, of 2020. And so the graph shows the evolution of the GDP nowcast over time as more data accrue. So for instance, the first point is published just after the release of the GDP for 2019 Q4. And then after the second point, then it's an update following the release of the employment data for January. And so after that, there are updates every time new data are published. And we can see that mid-April, there is a big drop in the GDP number. Well, this is because the industrial production data started to show then the extent of the restrictions that the government put in place for the coronavirus pandemic. So this started to kick in mid-April. And so in this work, what I'm doing is, my work is motivated by two facts. The first one is that this related series that we use to nowcast GDP, well, they are useful not only to have an idea of the GDP number, but they are also useful to have an idea of the uncertainty that we are going to attach to this GDP number. And so the idea is that if there are large forecasting errors in series like unemployment, and that these errors historically are linked to large forecasting error in GDP, then we should update our uncertainty attached to the GDP nowcast when we have large forecasting error in unemployment. So that's the first motivation. And to do this, we can model, the variance of the conditional distribution. In order to communicate uncertainty when we produce forecasts, we usually use a density function, which is attached to the prediction. So we have the location or the conditional mean here, which is the dotted line 0. And then we have the density, which represent then the likelihood that we attach to the various numbers. And so in the red line, it's a scaled Gaussian distribution with scale parameter equal to 1. And then in the blue line, I'm showing the same distribution, but with a scale parameter equal to 2. And so we can see that the scale parameter control the dispersion of the density function. And we can see that then by increasing this parameter, we have a greater uncertainty, which is symmetric on both sides of the distribution. So with Nowcasting method, we typically capture the relationship in the conditional mean of the series. But if we then capture also the relationship in the scale parameters, then we can quickly update the uncertainty attached to the GDP nowcast when we observe related series. So that's the first motivation. That's to model also relationship in the scale, not only in the location and conditional mean. The second motivation is that nowcasting uncertainty actually is, well, there is evidence that macroeconomic data are not normally distributed. So this can be because then the conditional distribution is asymmetric, or it can also be because then there is a greater likelihood of extreme observation. So the conditional distribution is fat-tailed. And the asymmetry can also vary along the business cycle. Typically, when we enter a recession, and this is illustrated well with the coronavirus last year. In April, we knew that the GDP number was going to be negative, but we didn't know the extent of the drop. But what was sure is that the GDP number was never going to be very large. So there was this asymmetry in the sense that we expected large negative observation, but not necessarily positive observation. And for this, it's useful to model a shape parameter which controls the skewness of the distribution. So here I'm illustrating, like before, the normal distribution with the red line. And then the blue line shows a distribution with this, which is skewed to the left side. And so this is very useful to capture the uncertainty when at the beginning of a recession, for instance, because then we put greater, there is a greater likelihood of negative observations, but then the chance of a positive outcome decreases significantly. So that's the second motivation. So in this paper, to capture the relationship in the series, I'm using a dynamic factor model. So in dynamic factor model, then we use a small number of common factors, common to all the series, in order to capture the cross-sectional dependencies. And we assume that conditional on these factors, then the data are independent. And to model the non-Gaussian feature in the data, notably especially the skewness, I'm using score-driven methods. So score-driven methods are very similar to Kahneman filtering methods, but the idea is that we set a predictive model for the data, and conditional on this model, then the data can come from any type of distribution. So we are not constrained to the normal distribution. And the main contribution I'm making here is that I'm exploring the benefit of modeling a common factor, not only location or conditional mean, like it's typically done, but also in the scale and shape parameter of the data. And when we have series which are observed on different frequencies, then and we want to model relationship in the scale and shape parameter, then we need to take this into account. So I'm showing, notably here, I'm showing that if the model is Gaussian normal, then there is a convenient approximation to temporally disaggregate the scale parameter and having a common scale parameter to each series. Then to investigate the benefit of this approach, I'm using US real-time data from the Philadelphia Fed. And I will show you also specifically what happens at the beginning of the coronavirus pandemic. So the model is a score-driven model. So for this, we need to, YT is the represent the observation vector, and M is the number of series that I'm modeling. Here, I will be modeling 4 series. So I will have GDP, industrial production, unemployment, and the weekly economic index. So I have 4 series, and then I need to set a conditional distribution for this data. Here, I'm assuming that conditional on the the dynamic factor model, the data are independent, so I can just add the log likelihood of each series. And the interesting thing here is that I can have a conditional distribution distinct to each series. So I can have GDP, for instance, which is fat-tailed, but the related series which are Gaussian. For the conditional distribution, I'm using an asymmetric student T distribution. So depending on the parameter, this distribution encompasses the normal distribution, the student T, the skew T. And the interesting thing with distribution is that we can have distinct tail parameters. So for instance, the left tail can be fat-tailed, but not necessarily the right tail, which controls the positive observation. So this asymmetry is also interesting. When I'm estimating the model, so because it's a nowcasting exercise and the data are not released at the same time, when we are estimating the model, some of the observations are missing. And in order to account for this, then we have this this dummy variable. So when an observation is missing, the log likelihood is simply doesn't affect the total log likelihood. So estimation is straightforward and is done with maximum likelihood. So then I need to set a model for the location, scale, and shape. And the parameters in this estimate, I'm dividing the location, scale, and shape into different unobserved components, so a trend and the common components, which I will put in FT. And then the learning mechanism here, the dynamics in the model come from the conditional score of the log likelihood. And then the conditional score is just weighted by the ESCoE in order to improve estimation. And so the score here is it's what drives the GDP, the estimate of GDP and of the uncertainty. And it's driven by the prediction error, because the score is a function of the prediction error. But the interesting thing is that depending on the estimated distribution, it might be nonlinear. So I'm illustrating this fact here. So for instance, so in the top left panel, I'm showing the density function. So if the density is normal, then it represents the red lines. We can see that the scale score function, for instance, for the location, which controls the conditional mean, is linear. So if we have very extreme observation, then this will be reflected as such on the model parameters. But if the model is fat tails, for instance, we can see that extreme observation are down-weighted. So this is interesting if we think, for instance, that these extreme observations are observation errors, because then they do not affect our estimates. But if these extreme observations are not observation errors, like last year, for instance, the large drops that we've seen in industrial production and all macroeconomic data really reflected a downturn in the activity. And if we want this to be reflected in our number, then here it might not be advantageous to have a fat tail distribution. So what I will be doing is that I'm constraining the related series to have Gaussian tails in order for the signal to be reflected as such in GDP and not have this downweighting. But the conditional distribution of GDP can be fat tail. So at the end, the uncertainty can have, I'm accounting for extreme value in the uncertainty. So for each of the parameters, the location, scale, and shape, I'm modeling a trend and a common component. The common component in all these series, the trend will capture the long-term variations, and the common component is useful to capture the short-term variations which are common to all series, like an economic crisis, for instance. And then this unobserved components, so the trend and common components, they need to be related to the location, scale, and shape parameters. And here it's a bit tricky because some series are quarterly and the others, the related series, are monthly. And the location of a monthly and quarterly series cannot be, so because the common model can be either monthly or quarterly. So the idea here is to model the common model to be monthly, and then the the components. So for instance, the location needs to be aggregated to quarterly components for the GDP, for the quarterly series. For the location, this is straightforward because, well, there is a paper by Mariano and Murazawa who popularized this approximation for the data, which can be translated directly to the location because there is a linear relationship between the location and the data. But for the scale parameter, then it's more difficult because there is not a linear relationship between the data and the scale parameter. So we cannot use this approximation. But starting from a similar approximation, it's possible to derive a new approximation, which I'm showing in the paper, if you're interested, in order to disaggregate temporally the scale parameter.
Sorry.
Yes, sorry.
Sorry, Paul, you have 5 minutes to go.
Okay, thank you. So this approximation can be used when the data are Gaussian or normally distributed. But if we want the data, each series to be not to be normally distributed, then it's difficult to disaggregate temporally the scale parameter. So what I'm doing here is that for this model, I will be aggregating the series to rolling quarterly series in order to model the common parameters. For estimation, I'm using maximum likelihoods, but I'm using weighted maximum likelihood by Blasquez and et al. Here it's interesting because GDP is observed only once a quarter, but the related series are observed monthly. So when GDP is not observable, it doesn't affect the log likelihood. And in this sense, there is an implicit downweighting of the GDP series, which is a bit annoying here because the series in which we're interested in is GDP. So in order to account for this, we can include this weighting factor, W, which will downweight the log likelihood of the related series. So here I'm just using a factor of 1/3 in order to put the likelihood of GDP and the related series to the same level. For estimation, I'm using GDP, industrial production, the weekly economic index, and weekly index of working hours, and the weekly economic indicator. I'm doing the estimation in real time using the vintages from the Federal Reserve Bank of Philadelphia. And I'm rolling the real-time estimation exercise from 2000 to 2020. So here I'm just showing the data. I'm comparing 6 different models. So 3 models do not feature the common factor in scale and shape parameters. And then I'm comparing this to 3 other models, which do include then common factor in scale and shape parameters. So I'm showing that if we include common factor in scale and shape, we have an improvement in the log likelihood attached to GDP. But this is, so here I'm just showing the estimation using the entire data. It's not a real-time estimation. This is useful in order just to see if we get, if the unobserved component that we get do make sense. So here, for instance, I'm showing the common component in the scales, and we can see that there is an increase in the scale components at the time of the typically economic recessions, so the financial crisis and the COVID period. Here is just the estimate of the location. Here is the estimate of the shape, so the skewness. The interesting thing is that we get, in terms of recession, the skewness typically jump, which means that this distribution is skewed toward negative values. And here I'm showing the results from the real-time estimation, and that's the nowcast for March, so for the first quarter of last year. And the interesting thing here is that the model, so model B, which include common factor in scale and shape, we are able to capture this, this asymmetry toward negative values, which is really interesting. And we do not get this if we do not model a common factor in either the scale or the shape parameter. Then for the second quarter of last year, which is the last quarter in my estimation period, we do get also an increase in the uncertainty when we model common factor in scale and shape. There are periods in the second quarter in the nowcasting exercise, there are periods where actually the predicted distribution is completely flat. And we could think that this is, so actually we cannot make any meaningful prediction, but it just means that from the data, It's just difficult to have any idea of the GDP figure, which in my view, it's having a flat distribution like that. It's more, well, it's better than having a distribution which is too precise on a given number, and then this prediction will be wrong. So here I'm just saying that sometimes the model is not able to provide a precise idea of the GDP number, and this just means that the environment is just too uncertain. And so I will conclude by saying that, so in this paper, I'm exploring the benefits of modeling common factor in scale and shapes, and I'm showing that actually in period of recessions, these two components are useful, not necessarily in normal times, but in period of recessions. And the other interesting things as well is that modeling 5 tails in the related series from which we are getting our signal is not necessarily useful, because then the signal is downweighted and it's difficult to capture important variation in the data. Thank you.
Thanks, Paul. So we have time for questions. Does anybody have any questions for Paul? Just unmute your mic if you have any questions. Does anybody have any questions? You can either unmute yourself, you can ask, or just put a question in the Q&A.
I think if nobody has any question, then we can maybe go through the next presentation, and if we have time at the end and questions, then we will go through them.
Okay. Okay, seems like there's no questions, so I guess we can just move on to Andrew's presentation.
Okay.
Yeah, so I probably should have mentioned, but yeah, so you can type any questions on the Q&A. All right.
Okay, everyone can see the slides?
Yep.
Okay, great. Well, thank you everyone for coming. So this is a joint paper with a former RA of mine, Trace Levinson, when he was working at the Fed with me. So I still work at the board. So of course the usual disclaimer applies. Oops. Okay, so it's a little bit of background. So the Fed economists, RAs, the staff. So we're actively engaged in forecasting the macroeconomy, and so we produce forecasts for each meeting of the Open Market Committee. These have been called green books or teal books. They're pretty well known. They're hosted on the Federal Reserve Bank of Philadelphia's website. We post our projections of the economy, including GDP. What this paper is going to do is create a new data set of the Fed staff forecasts. We're going to be creating a data set of the real-time projections of the economy by the Fed staff between the green books and teal books, which I'm going to be referring to as our high-frequency forecast data set. And so we're going to use these data to try and test something which I've been asked many times by the governors of whether or not the Fed staff is doing well at actually forming our projections. Obviously, we want to be doing well since we're providing them with what we think is the best guidance that we can to say where the macroeconomy is going to be going. So specifically, we're going to be testing with using these new data, testing whether or not the Fed staff forecast errors are predictable. Now, when I say predictable, just so that we can fix ideas, predictable meaning, can you use a model to forecast the forecast errors? So I'm going to be using sort of two broad classes of models. The first one, I'm going to be using forecast provisions to try and forecast errors. So you can kind of think of forecast revisions themselves as sort of an aggregation of information. So for example, if there's positive news on GDP, the Fed staff, we revise up our projection for GDP. That implies that whatever information that has accrued between the last forecast and the current forecast should be on net positive. So it's an aggregation of information concept. And similarly, when I was using a financial market index, this again is sort of a similar aggregation of information routine where hopefully financial markets are at least somewhat efficient in capturing information on the macroeconomy. So ideally, forecast errors are not predictable. So predictability can imply that either the forecasters are not using all available information, or they're conditioning on the wrong information, or there's some model misspecifications going on there. They're not interpreting the signal from the appropriate data series appropriately. So what we find using these new data is we do find some evidence of our Fed staff forecast predictability. Specifically, we find that the GDP nowcasts tend to revise too little in response to incoming information. So if we, the staff, get positive news on GDP, let's say we revise up the projection, what we should have done actually is revise up the projection even more than we actually did. And we find sort of the opposite result for inflation. We find their inflation forecasts tend to revise too much in response to incoming information, though the evidence is a bit weaker. Okay, so on the data, we just collected a bunch of archived documents from random internal sources. They're documented in the appendix to the paper. But we basically tried to use these archived documents to create a real-time account of what the staff was thinking about the economy, in addition to the well-publicized projections of the staff in the green books and teal books. So all of the data and code that we use for this paper is posted on the Fed site. You can download it, use it for your own research, etc. So I'm hoping what that means is that people will use the data, because the reason why we undertook this project is because we're trying to inform the governors as best we can about what's happening. And so obviously we want to be a little bit introspective in that regard and try and figure out whether we're giving them good information on the economy or not. And also, I'm hoping that means my code is correct. And if someone can, verify that and find an error, that would be great as well. Okay, so for new forecast data, so what do we actually have? So we've got US GDP growth, real GDP growth, and core PCE inflation, the periods over 2001 to 2011. We have 1 quarter backcast through 2 quarter ahead forecasts. And so the main contribution here is, again, we're improving the frequency. So green books and teal books, at least in recent years, we're posting 1 for each meeting of the Federal Open Market Committee. In recent times, there have been 8 of these per year. And so we're improving the frequency. So roughly speaking, we have weekly GDP forecasts. So about 6 to 7 times as many GDP forecasts in this data set as there are in the teal books. And roughly semi-monthly inflation projections. So about 3 times as many inflation forecasts as we do have in the teal books and green books. Okay, so just so we can visualize what's going on here. So this is a plot of all of the green book forecasts for GDP for the current quarter, or the GDP nowcasts, represented by these green triangles. And what we're doing is we're filling in the gaps between the green triangles. So we're trying to create a real-time projection of what the staff was actually thinking about GDP. And we do the same thing for inflation. So this is a chart of all of the green book inflation projections over this time period, and we're filling in the gaps between the green books here. Okay, so a couple things we can do here is we can create sort of real-time analysis of what the staff's forecasting performance was. So this is a chart of the staff's RMSE. So how you read this is going from left to right is the weeks to the beginning of the quarter, where week 0 is the first week of a particular quarter. So for example, for Q1, that would be the average RMSE for staff forecast made in the first week of January. And for Q2, that would be the RMSE for staff forecast made in the first week of April, et cetera. So the the gray shaded area in this chart are when the staff is making GDP nowcasts, so between week 0 and week 12, roughly speaking. And the dashed vertical line labeled BEA release is the approximate date of when the Bureau of Economic Analysis releases its first estimate for GDP for the previous calendar quarter. So that typically happens, again, as Paul mentioned, typically happens once about 4 weeks after the reference period ends. So for Q1, that would be like roughly the 4th week of April. For Q2, that's roughly the 4th week of July, et cetera. So what we can see from this chart is that there's a steady decline in the RMSE of the staff GDP forecast as we get more and more information, as we move closer and closer to the quarter. And there's an acceleration in the decline of the RMSE about when the quarter is open. So what that tells me, at least, is that the nowcasting signals are particularly useful for decreasing the RMSE of the staff GDP forecasts. The other thing that I also see is that, oh, sorry, I should have mentioned also, the truth in this chart is the BEA's 3rd release estimate. So that's typically released 3 months after the quarter closes at the end of that month. So for Q1, it's typically released at the end of June. For Q2, that's typically the end of September, et cetera. And so at least what I see here is that even, so there's an acceleration in the decline of the RMSE when the quarter is open or when there's a nowcast. And also, even after the BEA releases its first estimate, which again is the end of the month, immediately after the quarter closes, even after it releases that estimate, the RMSE continues to fall, which tells me that the first release estimate is not a sufficient statistic for the 3rd release estimate. Okay, so we can do that for GDP, and you see a kind of a similar thing for inflation. There's a steady decline as you get closer and closer to the quarter. The fall in the RMSE accelerates once the quarter is open, and the RMSE continues to fall even after the BEA releases its first estimate of PCE prices or core PCE prices. Okay, so we're using these data again. We're testing to see whether the staff forecast errors are predictable or not. So there's a lot of ways to go about analyzing these new data, an infinite number of ways. And so Trace and I, when we were starting this paper, we wanted to mitigate 2 potential psychological biases. So the first is hindsight bias. So in any of these sort of retroactive analyses of forecasts, or even programs for that matter, we as like the researchers have accumulated a body of information since the point where those projections were made that may subject us to particular biases or particular ways of thinking about things that are not correct. You can also kind of think of that as like the researchers, or us in this case, have more information than the people did when they were forming the projections in the data set. So we want to try and avoid any potential biases in our analysis that come from that particular facet. The other thing is a little bit more idiosyncratic to the 2 of us, which is that well, Trace was a member of the Fed staff. I'm still employed by the Fed. So that, because of our employer, it could induce some type of bias as well. So we may think, okay, we both have some vested interest in informing the Board of Governors. We may be inclined, ceteris paribus, we may be inclined to say, look, we don't want to find any inefficiencies in the projections. We want to find that we're doing everything well. If you find something bad, that could be an indictment on our colleagues or our way of thinking about things, and we want to try and avoid that potential pitfall and say we want to just give what we think is the most accurate analysis possible. So there are these 2 psychological biases. I'm sure there's more, but these are the 2 that we were thinking about at the time. I'm trying to avoid these. So how do we get around these problems, or at least mitigate these problems? So all the analysis here, we conducted using a pre-analysis plan. So we basically wrote out the data cleaning steps, the models, et cetera. before we actually ran any analysis. So we wouldn't be subject to this sort of retroactive thinking of, oh, we saw model estimate X. Maybe we should go about and change the model. No. We're going to write down the models beforehand. We're going to give one shot at everything to give as clean an analysis as possible. So that, of course, gets rid of things like pre-testing and things like that. And it's registered on the Open Science Framework timestamp, so you can download the plan for yourself and see when we actually came up with all this stuff. Okay. So the first set of muscles, we're just going to do something really, really basic. So these are sort of Mincer-Zonowitz regressions or Nordhaus regressions. So in this equation, so y is the actual value of the macroeconomic variable that we're forecasting. So in this case, it's either BEA GDP or core PCE, real GDP growth or core PCE prices. So y is the actual value, which we're taking as the third release estimate. So again, that's typically available approximately 3 months after the quarter closes. Y hat is the staff forecast of y. T plus H, it's a forecast of quarter T made H quarters ahead. And the contribution of the data set that we constructed is this tau index. So we're able to look at staff forecasts within the quarter to try and get multiple observations or multiple forecasts of a particular Y per quarter. And then delta, of course, is just the change. Okay, so basically on the left-hand side here, what you've got is a forecast error, and the right-hand side is a forecast revision. And you're just looking for the correlation between the revisions and the forecast errors. It's very, very simple. So beta in this model implies over or under revision. So a positive beta means that on average, the staff forecast is under revising. So for example, for GDP, if we were to get positive information on GDP, revise up the staff forecast, so delta Y hat is positive, yet beta is still positive, that means that on average, that forecast is under predicting. So you should have revised, or we should have revised the projection up more than we actually did. And similarly for negative means over revision. So the critical assumption here in this model is that we're evaluating the staff projection based on RMSE. I know there's a big literature on what the loss function is of central bankers or forecasters or whatever, asymmetry, whatever. From my experience working in actual macroeconomic forecasting, I'm actually not entirely sure if the forecasters have like a particular loss function in the back of our heads. It certainly hasn't been stated explicitly to me. So you can say, well, evaluating in terms of RMSE, that's not right. You should be using, you should be overweighting these negative observations or whatever. That's totally fine. You can use the data yourself and do that analysis. This is purely going to be an evaluation based on RMSE. Okay, so what do we actually find? So we find that the current quarter GDP forecast or the GDP nowcast on average tend to under revise. They should have been 52% larger than they actually were. And the inflation backcasts tend to over revise, which is kind of weird to me because at that point you have all the nowcasting indicators, and in some of the observations you have the first release estimate for core PEC prices for the previous quarter. So what that's telling me is that there could be perhaps a psychological bias by the staff to sort of jump the gun on some of these revision indicators. Okay, so this is sort of predicting average forecast behavior, but the key behind, or one of the reasons why we constructed this data set, constructing all of these projections for GDP and inflation between the green books and teal books, is that we want to look at time varying behavior. We want to see whether or not the staff is more inclined or less inclined to over or under revise as a function of when the forecast is actually being created. Basically analyzing our behavior between the green books and the teal books. Okay, so what do we do? The first pass at this, we construct or we estimate this equation where the new terms here are indexed by this indicator I tau, where I tau is just a dummy for whether or not the projection was made in the 2 weeks just prior to a FOMC meeting. So the reason why we did it this way is because, at least from our experience creating the forecast, is that we, the staff, are basically paying what I think is increased attention to the economy around when the interest rates are being set. There could also be psychological biases here as well, but there's something about the way that the staff creates its projections or updates the governors that's inherently tied to the open market committee or open market committee meetings. So we may think that the staff forecasting behavior is different when you're near an FOMC versus not. I know there's a ton of other ways you can go about this. You could look at, say, the composition of the board members. You could look at turning points, recessions, et cetera, et cetera. But what we were trying to answer for the question, which was actually posed to us by the governors, was, are you actually giving us the correct information? And what we thought was the appropriate metric was at what if the forecast was made at a particular point with regards to the FOMC meetings, is that forecast better or worse off than it otherwise would be? And so what this model is doing is it's testing for basically time varying behavior between forecasts that are made close to FOMC meeting versus far away. Okay, so of course, the dummy is completely arbitrary. I'm not using indicator saturation or anything like that. So what we're doing is we're using a pre-analysis plan here. We only run one version of this. We're not testing a bunch of different versions of trying to show you a p-hacked result, basically. This is just one pass at it. Okay, so what we find is that the inefficiency in the staff's GDP forecasts are concentrated in those projections that are close to, that are far away from the FOMC meeting. So it appears that the GDP forecasts, at least, that are made close to the FOMC meeting are efficient. And then what we actually find is that, roughly speaking, even for the forecasts that are far away from the meetings, the growth rates are wrong, but the levels are about right. For inflation, we actually find the exact opposite again. So before I said on average, the inflation forecasts are tending to over-revise. What we actually find is that inefficiency is concentrated in those projections that are made close to the meeting. So there's something about potentially perhaps the inflation forecast may be getting too much scrutiny when the interest rates are about to be set. Okay, I'm almost out of time, but I just wanted to go very briefly over some speculation. So one thing we wanted to ask is whether or not there's additional information that the staff could use to improve its projections. And so what we did is we created just one measure of outside information from financial markets. So this is a weighted average of outside forecasters, forecast errors mixed with S&P 500 returns. So it's kind of synthesizing market information combined with the information from other forecasters. Obviously, there's a bunch of arbitrary features with creating an index such as this. So again, we're using a PAP here. We're only running it one time. We're not trying to find a particular result. So this is what the index looks like. I guess there's two features that stand out to me. So the first is that it's heteroscedastic. The variance goes up in the recession, and it actually stays elevated even after the recession. But the other thing is that it's actually mean zero, thank goodness, because there's actually nothing in the index that actually we force it to be mean zero. But it's mean zero and heteroscedastic. We just add this index to our baseline models. And then again, we separate it out between for forecasts that are made within the 2 weeks before the meetings versus not. And what we find is actually this sort of synthesis of outside information plus financial market information actually does predict the GDP forecast errors, but it does not predict the inflation projections. Okay, that's all I have. Again, the data are actually posted on the Fed's site, the working paper version for this paper, or on my personal site. You can just download them and use them for yourself if you'd like. Okay, great. That's all I've got. Thank you.
Thanks, Andrew. Does anybody have any questions? There's no questions on the QA. There's no questions on the QA, so I'm not sure. Just again, does anybody have any questions for Andrew?
I think that means we can move on then.
Yeah, okay. Yeah, okay. I'll just move on to my presentation then. Yeah. Okay, so this work is joint with a couple of my colleagues at Strathclyde, Gary and Stuart, and also James from the Federal Reserve from Cleveland Fed. So I should also mention that the usual disclaimer for James applies too. Okay, so the main goal of this paper is basically to produce monthly true GDP estimates during the pandemic period. So this paper basically builds off our earlier work, this reconcile estimates of monthly GDP in the US. So this is already out as a ESCoE discussion paper. So basically in our earlier work, what we did is we proposed a model, a mixed frequency state space VAR model with this ADNS measurement restriction, measurement error restriction within the model. So I'll talk more about this ADNS measurement error restriction in the next slide, but basically this measurement error restriction allows us to reconcile these two GDP measures, that is GDPE, the expenditure side, and GDPI, that is the income side, and it allows us to produce monthly true GDP estimates. So, this, in our current paper, basically what we'll do is we're taking what the proposed model that we've done in our earlier work and extending these models by different error specifications to accommodate the pandemic period. So basically what we do in terms of methodology is we're sort of combining two methods or two approaches. So the first approach is this ADNS, or this Aruba et al. Journal of Econometrics paper, where they proposed this dynamic factor model where they reconcile the two GDP measures, and it allows them to produce a quarterly true GDP estimate. However, as I mentioned in the beginning slide, we want to now cast monthly true GDP estimates. So as a result, we need to use some sort of mixed frequency method. So basically, in order to produce monthly true GDP estimates, we have to use, we use the mixed frequency methods of Shofadi and Song, this JBES 2015 paper. So in a sense, our methodology or framework is a combination of the ADNS, this Aruba et al, and Shofadi and Song. So basically what we do is, the main gist of our model is we're estimating a mixed frequencies state space VAR, where we incorporate this ADNS measurement error restriction that is proposed in this paper, Journal of Econometrics paper, to produce a monthly true GDP estimate for the US. So I guess, why do we care? You might be asking, why do we care about producing true GDP, this true GDP estimate? So in theory, both these two GDP measures, in theory, should be equal, but the US, the US Bureau of Economic Analysis, they note that actually these two GDP measures are derived using two different sources. So in practice, these measures are quite different, and this is due to measurement error issues. And also, within the literature, there has been studies by Naririte that actually shows that using these two GDP measures can lead to two different empirical conclusions. I guess a good example is this study by Naririte 2010 that actually shows that GDPI is a better early predictor in recessions compared to GDPE. So therefore, it's sort of, our main motivation is that you sort of need a true GDP measure to capture the dynamics of both the two GDP measures, because if you just use one of these GDP measures, you're sort of missing out on the dynamics of the other GDP measure. So I guess that's the main motivation why a true GDP measure is important. Okay, so basically in our previous work, what we did is we could rewrite the original ADNS model into a mixed frequency VAR with one lag. So basically, this equation one, this is sort of a structural VAR with one lag. So you can sort of think about this A matrix is the contemporaneous matrix where you have one on the diagonals, and on the left part of the matrix, the off diagonals, it's non-zero. And then this B matrix, the VAR coefficients, these are they're sort of restricted, some of the coefficients restricted to reflect the ADNS model. And then this is the variance is just a diagonal matrix. So here, one of the beauties of writing this VAR in structural form is that you can estimate this by equation using the Carriaro et al. Approach. And this is just for computational efficiency. So if we as I said, this is a mixed frequency VAR. So our YT vector is a combination of monthly variables and quarterly variables. So in this case, this XT, these are sort of monthly economic indicators. So these XT are basically the monthly economic indicators from Shofadi and Song. So Shofadi and Song, they estimate a monthly quarterly VAR, and they have, I think, 8 monthly indicators. And basically, we just use the same monthly indicators for Shofadi and Song. And then we also include, which is also in the Shofadi and Song paper, the monthly unemployment rate. So the reason we include the monthly unemployment rate is within the ADNS paper, they include the unemployment rate as a way to identify the model. And here you can see that both GDPE and GDPI are only available at the quarterly frequency. So here our true GDP, this GDP, that's our true GDP estimate, and that's basically our unobserved latent variable. So this mixed frequency VAR model, we can sort of think about it in a sense, it's a Shofadi and Song mixed frequency state space VAR model, but we impose the ADNS measurement restriction in our model. So one of the things that we have to do here is we need to impose some identification on the contemporaneous matrix A, and we just impose the noise restriction. So basically what this noise restriction means is that it just means that the volatility of true GDP is going to be less than the volatility of GDPE and GDPI. So basically in our current paper now, what I'm doing is, because in our original earlier work, we just assumed homoscedastic errors. But in our current paper now, we extend our original model via different error specifications to accommodate the pandemic period. So basically, this is our general specification. So here, we can write the error term as a normal, given some lambda, unobserved lambda, and a Scossive volatility term. This Scossive volatility term follows a random walk. So basically, in our paper, what we do is we make 3 assumptions about lambda I. So if lambda I is equal to 1, we just get back to a normal Scossive volatility errors. So our original model has Scossive volatility errors in our model. And our second assumption is we assume that this lambda follows an inverse gamma. And this is sort of implying there's fat tail stochastic volatility in the errors. And our third assumption is we assume this lambda follows this SV outlier adjusted errors from Stock and Watson 2016 restat. So that's our third specification. And then also what we also do is we also consider our second and third specification without SV. So basically we have fat tails, but no SV, and we have the outlier adjusted errors, but with no SV. So these, this is basically what we're doing in our paper to accommodate the pandemic period by just extending our model by these different error specifications. Okay, so basically, what I'm going to do for the empirical results is I'm only going to show we basically do a nowcast throughout the 2000 for each quarter of the 2020 year, but due to time constraints, I'm only going to show the results for the nowcast for 2020 Q2 and 2020 Q3, as that's probably the most extreme events. So basically, this table here just shows the sort of the nowcast predicted densities based on these, so the three models, and also relates to the different vintage, the nowcast predictive variants are based on predictive densities based on the data vintage. So for example, this KMP, that is our original KMP model with just homoscedastic errors, and in this December 19, that is based on the December 19 vintage. So in this sense, these are the 4 moments that summarizes the predictive nowcast for that particular 2020 Q2 using that data vintage and so forth. And here, this is our model with only fat tails. There's no SV. And similar, this is the outlier adjusted of Stock and Watson, but no SV. So I guess the common theme is that as we go through each data vintage, sort of our mean gets updated. So sort of probably April, we start seeing that big drop. And similarly for all the other specifications, we see that. I guess probably in May, we see sort of across the 3 specifications, we see the variance increase. Probably one thing to note is probably the fat tails and the outlier adjusted, the variance, especially on the June data vintage, the variance explodes, sort of not explodes, but it's quite high compared to the homoscedastic. So that's sort of saying there's a lot of uncertainty around that nowcast for true GDP for that particular data vintage. And also, I think one reason that could be causing this large variance could be there's a big, because in the ADNS model, they use the difference of unemployment. And I know during that time, the difference in unemployment was quite large, and that could be influencing the nowcast too. And so basically, this is the same thing, nowcast for 2020 Q2 for true GDP, but now we incorporate stochastic volatility in the model. So this is just our original model with SV errors. This is our original model with SV fat tails, and then the SV outlier adjusted errors. So similarly, you do get, I guess, one thing, the June, actually, yeah, the variance, especially for the SV, goes quite crazy. So like I said, it could be because of that big shift in unemployment, and because we used in the ADNS model, we used the unemployment to identify the model, and that could be one of the reasons. So But I guess the whole theme is that as we progress through each data vintage, we get more and more negative numbers. And then the next, this nowcast is for the 2020 Q3. I guess similarly sort of see that in May, it's from like March 20 to May 20, based on those vintages, it's still a negative number. And it's only probably from like the July vintage, then the true GDP number becomes more positive. So similarly, again, we have quite large variance during the real negative numbers. So this is sort of saying, again, the nowcast for true GDP is quite uncertain during those periods. And this is the SV. Again, we sort of get some crazy number for the June. So yeah, again, there's a lot of uncertainty with it. Okay, but I guess a common theme with these nowcasts, I guess what we can draw out is actually our original KMMP model, where we just have homoscedastic errors, is that it actually does relatively well, because you don't see, yes, maybe there might be a big jump in variance, but obviously most of the time seems to be okay, the nowcast. So this is my last, I guess, sort of empirical result I want to show you is sort of based on what true GDP, our true GDP estimates based on the current vintage. So this column here, this is our KMMP model, where we have the mixed frequency model, with the ADNS, we can produce monthly true GDP estimates. So the Philadelphia Fed have also like a true GDP estimate, which is called GDP plus. So basically the Philadelphia Fed GDP plus estimate, the numbers, it's basically the original ADNS model, the quarterly model. So basically what they do is each time GDPE and GDPI is released, they just run the ADNS model on it and then produce a GDP plus measure. So this is based on the April 2020 vintage. So I guess I just want to show there may be some instability in the original, I guess, the ADNS model. So for example, if you look at the 2020 June measure, so this is like 2020 Q2. So the observed GDPE and GDPI measure was about 38%. So it's 38 minus 38%, 39 observed. But the Philadelphia Fed, they said true GDP was minus 15%. So I'm not sure, but this is quite extreme. But in terms of our model, we sort of get something close to the observed GDPs measures. So I guess, and looking at the third quarter of 2020, the September 2020 Q3, so they're saying true GDP was about 9%, but GDPE and GDPI were observed at around 28% and 21%. So what our model says is about 22%. So based on these figures, I'm not implying anything, but I'm just implying there could be some sort of instability in the original model. But in our model, it seems like our true GDP measure sort of reflects sort of the actual observed. So one of the reasons could be is because we have monthly indicators in our model, and it could be the case that our monthly indicators sort of disciplines the model. So we sort of get a true GDP estimate that is sort of close to the observed measure of these two GDP measures. Okay, so I just conclude is basically what we do is we extend our original KMMP model to via various different error specifications to accommodate the pandemic period. Actually, basically the main takeaway is basically we sort of find that actually our original model with the homoscedastic errors actually is very robust in producing the outcasts of true GDP during the pandemic. And this could be because of the measurement error restriction that we impose for the ADNS by the ADNS. And also, like I said, it could be another thing is like we have monthly indicators and that sort of disciplines the model. And I guess, as I noted, when we use a more flexible error structure, we sort of find that the predictive densities are more larger. Okay, and yeah, so this paper will be published in upcoming special issue in the National Institute Economic Review. So if you want more details about this paper, and also you can check out my personal website if you want the latest monthly true GDP estimates for the US. Okay, and yeah, so that's it. So I'll stop sharing my screen. I guess if there's any questions. Yeah, so so Florin has a question. I think if you can unmute Florin, you can probably just, we have time, so you can just, how do I unmute people?
Thanks.
Yeah, sorry, yeah.
Thanks a lot for this presentation. Actually, I have two questions.
Yeah.
First one is going back to my own experience working with models which are essentially mixing up heavy-tailed errors and stochastic volatility. I tend to find evidence that you're actually not needing both features, but only one of them. And the problem really is that if you estimate the degrees of freedom parameter alongside the remaining model parameters, then those tend to become large because especially when you have a heteroscedastic model, these tend to become weakly identified. So the question is whether you have some sort of forecasting evidence for either GDPE or GDPI, which tells you which of the two features is important. And the second one is what sort of prior you're using to estimate the degrees of freedom parameter, because my experience is also that this typical uniform prior you tend to use is really introducing no information by definition, but what has been working well is a sort of a gamma style prior, which is really placing prior mass on smaller values of the degrees of freedom parameters.
Yeah.
Thanks a lot.
Yeah, so I think for the first question, we haven't done that in terms of basing the forecast on GDPE or GDPI. So that's actually a good I guess question and idea that we could look in the future. In terms of degree of freedom, yes, we do use a uniformed prior, and we actually we have to. So there were some issues with using that. I think we had to set the degrees of freedom to be greater than 5. If it was less than 5, we'll get in some issues that the variance explodes. So yeah, there are issues with that. Yeah, we find out. And I guess the next question is by Anna.
Sorry, I actually don't have a question because I've been surfing across sessions. Sorry, what I want to say is that if you guys wanted to talk more about, I know that this environment is a bit tricky for conversations. We're gonna have open channel for Zoom during the coffee break. So if you want to discuss more of the papers there, that's gonna be something you could do. Sorry for this interruption.
Nice. Okay, I think there's a question by Martin.
Yes, I'm afraid this is a rather general question. I'm trying to see how your model related to the early regression models that linked the residual, that explained no GDPE and GDPI by the residual error and derived fixed weights for combining them, which you could show were proportional to the ratios of the variances of the measurement error in each.
Yeah, so I'm not sure about that. Probably, maybe if James, probably my co-author James probably knows more about that than me. But I think what we did find is that we actually find that true GDP was highly correlated with GDPI. So it seemed, I don't know, correct me if I'm wrong, if James, but I think it seems to be GDP, the true GDP was highly correlated with GDPI. So it's sort of more weight. Yeah.
Thank you.
And Peter?
Yes, can you hear me?
Yep.
Yeah, I guess this question is for you or the prior authors, but there's several nowcasts of US GDP, and 2020 is a very difficult year for them to handle. One issue I have seen myself is that because the downturn occurs in the second half of March, a bunch of surveys were already finished. And so Q1 looks normal in some data series, but it wasn't normal if one catches the end of March. So I wondered if there is a broad survey or comparison listing them. You compensated for several specific issues, for example, the fat tails. And there must be a list. I've seen another case in which the undercounting of services it created a twist in the WEI, I think.
Yeah.
Is there a survey of them, and what made what 2020 struggles they had?
Yeah, I'm not sure about the surveys. Probably my co-authors probably know more better than me. Probably I think if there's a coffee session, maybe we can talk more about that. I'm not sure about the surveys, to be honest.
Thank you. I just mean a comparison, maybe not a survey.
Yeah. Okay. I guess the problem with, because we're measuring true GDP, it's a little bit difficult because there's no really, because that's unobserved. You don't really know the truth because it's quite difficult what is true GDP because that's unobserved. So it's quite hard. But if we're sort of now casting what maybe GDPE or GDPI, maybe you can sort of find an out term, but true GDP would, we're sort of now casting at unobserved. So it's quite difficult to determine whether our true GDP measure is correct in some sense.
I see. Yes. Okay.
I have one question for Andrew, if I can.
Yep.
So Andrew, when you analyze whether or not the errors, forecasting error can be forecasted, since you're part of the Fed, and then the forecast of the Fed, they do influence the decisions of the Fed. I'm wondering whether or not, do you account for the endogeneity and the fact that the forecast that you produce might have changed the decisions that the board took and actually affected the actual number? Or is it that your analysis is just in the very short term, and in that sense, the Fed has no impact on GDP in the very short term?
Okay, so I'm not sure whether you're asking whether or not like the response of the the governors is endogenous to the projections that the staff are making, or whether or not the forecasts that we're making are actually just are conditioned on a particular state. I think it's a combination of those.
Yes, because your analysis is for the governors, and then they make their decisions. So the forecasts they affect their decisions, which actually at the end might affect the GDP number. So depending on the forecast, then you affect the outcome. So do you take this into account when you do your?
Yeah, so that's always an interesting dilemma. So the way that the staff makes its projections, so all our projections are conditional projections because we don't want this sort of feedback loop to happen, where the governors themselves may be actually influencing the projections. Obviously, like we're providing them what we a particular set of projections, and so that their policy decisions may or may not be influenced by those. It's hard to say exactly. Which is part of the reason why like both the green books and all of the forecasts that I showed are all conditional on a particular policy path. So for the short term, the difference between like the conditional and the unconditional projection is going to be relatively small. I mean, for nowcast, like you have X percentage of the quarter that's already over, and so there's no way that the the conditional policy path can vary from what the actual policy path was. Obviously, it gets a bit more tenuous once you get further out. So I guess I would say, all the forecasts that I'm showing are conditioned on like a particular policy path, because there's this sort of like feedback loop that can happen.
Okay, thanks.
Is there any other questions? Do you want to ask the speakers? Okay, I guess it seems like there's no more questions, so I guess we should end the session, and then as Anna mentioned, there's the coffee break sessions that people can go and we can chat more about our papers if people want to.
Thank you. Goodbye.
Thank you for coming.
Thanks.